welcome back. Now, there are 5 things that needs to be. Okay, hi, welcome back. Now, there are 5 objectives of today's video. Now, in this chapter of work, energy, power, we're going to look at a few things. Okay, one of the main concept that we have to look at, which is objective number 4, is the idea of the work-energy theorem. Okay, basically how to solve all questions using the idea of the principle of conservation of energy. That is that energy cannot be destroyed or created, it can only be converted from one form to another. Okay, so what are the preceding 3 before we can go to the idea of the work-energy theorem? The first 3 that we'll be going through will be Ke, which is known as kinetic energy, Gp, which is known as gravitational potential energy, as well as our work done. Okay, the idea of work done is important, and of course when we study work done, then it will lead us to the idea of the work done against friction. Sorry, so let me erase this. It should be work done against friction. Okay, now the 5th thing that we are going to go through, that is the idea on power and efficiency. Okay, so now each of the section will take about 5 minutes, so brace yourself for the next 25 minutes. Okay, so without further ado, let's go. Before that, right, these notes I'll be uploading somewhere on Google Drive, so you can download the notes as well. Now, our first stop, kinetic energy. What exactly is kinetic energy? Kinetic energy has to do with speed. It is possessed by an object when it has speed. Okay, so let's say we are looking at an object here and it's like traveling at 3 meters per second. Does it have Ke? Yes. Okay, you look at another object, it's neither moving left or right. Okay, it's stationary at this point. Does it have Ke? No. Okay, so the idea of Ke is given by the idea whether something is moving or not. Alright, and this is so because the equation, right, is governed by this half mv squared, where m is the mass and v is the speed or velocity of the object. Now that's it, right? We want to look at something else. We want to look at the idea of the gain or loss, or basically known as the change, which is denoted by this symbol triangle in Ke. Okay, so the gain, loss, or change in Ke. Now, how do we calculate the change in Ke? We say that the change in Ke, right, is governed by this. Change in Ke equals to final Ke minus initial Ke. Okay, now change in Ke equal final minus initial. That is to say that, first thing, let me make this clear. 3 meters per second, right? Does it have Ke? Yes. Okay, so this is at position A. Now it later on starts to move and it eventually ends up here, but it's also at 3 meters per second. Okay, so has the speed changed? No. Does it have Ke at B? Yes. Okay, now our question, did it gain Ke? Okay, so let's do a quick math. Okay, so let's say the ball is 1 kg. Okay, obviously the mass doesn't change from A to B. Okay, so the Ke at A, let's take Ke at A, is half times 1 times 3 square. Okay, that gives us 4.5 joules. Now the Ke at B is also the same, it's half times 1 times 3 square, which also gives us 4.5 joules. Okay, and we take final minus initial, final Ke of course, minus initial Ke, right? Okay, what we have is 0 joules. Now what I want to emphasize here, right, is that when the object is at constant speed, okay, did it gain Ke? Answer is no. Okay, we realize that the speed, when it's constant, there is no gain in Ke. Alright, so when your speed is constant, there is no gain. Okay, let's do another example. Okay, so let's say in another scenario, okay, I'm going to do this in green. Okay, in another scenario, I have a ball 1 kg from A. It moves all the way to point B, and the ball remains of the same mass, of course. Now it starts from not from rest, okay, but say 1 meter per second, and it slowly accelerates to like maybe like 4 meters per second, as it goes from A to B. Now how do I find the change in KE in this case? Change in KE, right, is governed by the formula final KE minus initial KE. Okay, and this is actually half m4 square minus half m1 square. Okay, a lot of people would just take like half m4 square and say, oh, that's a change in KE. No, okay, you have to use this idea that we have to take the final minus initial. Okay, so we have to take the difference. We have to find a KE here, and then we have to find a KE here, and then we find the difference. Okay, if you're just going to find the KE at this point, okay, then you'll definitely end up with the wrong answer. Okay, because that is the KE at B only. Okay, what we want is the gain in KE or the loss in KE. Okay, so following this working, since the mass is 1 kg, right, we have 16 minus 1. Sorry, I mean we have half times 16 minus 1 times half, right? That will give us 7 joules. Okay, so I hope in this short less than 5 minutes you will understand the idea of gain and loss in KE. Okay, because with this, right, we are going to move on to the second idea, which is our GP. Okay, so the first one on the idea of KE is done. Okay, let's move on to GP now. Now the idea of GP, right, is while KE is governed by speed, GP is governed by height. Alright, so GP has to do with height. Now as the name suggests, right, it's potential energy. Okay, so potential energy is the energy that you potentially have. Alright, so let's say you are like going to throw a ball from a certain height, say of 3 meters, versus you are going to throw a ball from a certain height of say 0.1 meter. Now which one will land with a faster speed? Okay, by logic, right, or rather by our sensing, right, we know that the first scenario will have a higher speed at the end of the day when it's about to hit the ground, as compared to the second scenario when it's about to hit the ground here. Okay, this one would not have the higher speed. Okay, so obviously the idea of potential energy has to do with height. Okay, and we are talking about gravitational potential energy here. Gravitational potential energy. Alright, now it is really the potential energy, like the energy that is stored within here. The potential is able to release, right, as it goes down all the way here is higher as compared to this. Okay, so this is so because the idea for GP, right, is being governed by this equation, GP equals to mgh, where m is your mass, g is your gravitational field strength, and h is your height, which is in meters. Okay, so this is the idea for GP. Now same thing, we're going to look at the idea for change in GP. Now the idea for change in GP, right, is pretty straightforward as well. So change in GP has to do with the idea for change in height. Okay, so if I have an object, so let's say it's like a roller skating rink, right? Okay, where you start off here and then you're going to roll down, go up, come here, and then you're going to roll down again and come up here. Alright, so it's a roller skating park kind of thing. Okay, so this is the rollers. Let me draw it in my color. Okay, so this is the roller skater. Okay, it's going to skate down. Okay, now I want us to consider a few points. Okay, first thing, point A, the point where he's at. Point B, point C, point D, and let's just make this slightly more interesting. And point E. Okay, let's say E is the final platform. Okay, and I want you all to see that from A to D, right? From A to D, let's say this is like 2 meters, and from A to E, right, is like 1.5 meters. Okay, did the skater gain or lose GP in the entire process? Okay, so as the so for that to for us to work that out, right, is that change, so is it a gain or loss in GP? Now we need to consider a few things. Okay, first thing was the skater at A, right? So let's count the GP at A. It was something like mgh, where the h is actually 2. Okay, and the GPE at E is given by mg 1.5. Sorry, okay, mg 1.5. Okay, that's because at E, right, the height from the lowest point is 1.5 meters. Okay, so the change is also given by the same formula. Change in GPE, right, is given by final minus initial, and of course, since we are talking about GPE, is final GPE minus initial GPE. Final GPE is found in E, initial GPE is found at A. Okay, so we just have to look at the final point and the initial point, and then we can do a comparison. So what we have here is GPE at E, sorry, minus GPE at A, and what we have, right, will be mg 1.5 minus mg 2, and we will have negative 0.5 mg. Now, why is there a negative when this is a scalar? What does the negative mean? A negative means a loss. Okay, so is there a loss in energy? Yes, obviously, right? The skater is dropping in height. Look at where he was at point A. He was 2 meters above ground, and look at where he was at point E. He's at 1.5 meters above ground. Okay, so looking at these two height, right, we know that the skater, this guy, he has lost height in the process of going from A to E, and this makes sense. A negative 0.5 mg would mean that he lost GP in the entire process. So yes, indeed, he lost GP, and our answer mathematically confirms that because it's a negative 0.5 mg. Okay, the last thing that is interesting about GP that I would like to talk about, right, is on the idea of a reference point. Okay, so now reference point. What is reference point? Okay, reference point is the lowest height that we would want to see with regards or in context to a question. Okay, so it's the lowest point possible in a given question. Okay, now we have to define this reference point nicely so that we can be able to identify where is the final position and where is the initial position. Alright, so let's start off with something simple, right? I'm on top of a cliff. Okay, I'm gonna throw something down. Okay, I'm on top of a building. Okay, and I'm gonna throw something down from, say, at this level, right? And my friend's gonna catch it at the bottom. Okay, so where is the lowest point in this scenario? The lowest point is here. Let's call this the reference point. Okay, the reference point is special because the h is 0 at the reference point, meaning to say if I have an object here, the GP here can be written as 0 joules. Whereas if I'm like, say, 4 meters above ground, right, then the GP of this object here, right, is given by mgh, where the h is 4. Okay, now this is a simple one. Okay, so let's jump to a slightly more evolved one, where I think you see it commonly in your questions, maybe in a 10-year series or an assessment book, and that would be like maybe like a roller coaster going down and then going up again. Okay, so this is a very typical question. Your roller coaster start off at point A, eventually you're going to end up at point C, but you know you have to go through point B. Okay, so the roller coaster goes something like this, right? It goes from A, goes to B, roller coaster at C, and then goes down to, say, D. Okay, now at this point, right, where is our lowest point in this question? Okay, so pardon my drawing, but actually point D is on level ground. Okay, so the lowest point possible here, right, is B and D. And let's say this is like 40 meters above ground, and this is point C is like 30 meters above ground. Now what is the GPE lost as it goes from A to C? First thing, is it a loss or gain? Okay, so we see, right, at point A the height was 40 meters, at point C the height is 30. Okay, so obviously there's a shortage, there's a loss in height. Loss in height would mean that GPE is lost, okay, not gain. All right, so we'll come back to this question later. Okay, but anyway, let's find the GP at A first. Okay, let's find the GP that is lost. The GP at A is given by mg 40, right? And the GP at C, right, is given as mg 30. Now the lost is given by final minus initial, so it will be negative 10 mg. Now of course you don't have to write the negative, okay, you can omit the negative. You just need to know that it's a loss, and you're going to write loss in GP equals to negative equals to 10 mg joules. Okay, now I would like to ask, right, at this point, right, that if let's say I have a roller coaster, so it starts off at A, right, and then it goes down, hits B, and then goes up to C. Okay, at this junction, at this junction, when the roller coaster is here, okay, then we know that it has lost GP. The lost GP actually goes to, okay, there are a few things it can go, it can convert itself to. Okay, so it converts to, okay, first thing, if there's no air resistance or friction, right, let's say the question asks you to neglect those, okay, then very obviously the loss in GP actually converts to gain in KE, which is why the object at this point has a certain speed. Okay, obviously it can't be 0 meter per second. Like if it's at 0 meter per second, right, then the object will just drop down and everyone will just die in the roller coaster. Okay, but we are not so morbid. Okay, so we are obviously there will be speed. Okay, so there is speed, is definite. Now, so the loss in GP actually goes to a gain in KE. However, if there's friction or whatsoever, we need to write that the loss in GP actually converts itself to a gain in KE plus the work done against friction. Okay, which is our third point for today's video. Okay, so this is the idea for GP, and I'm going to go through the idea for work done now. Now the idea for work done is fairly simple. Okay, following just one rule. Work done, okay, the formula is given by force times distance. Now what is the rule here? The rule is that the force, the object that is being that is given a certain force, right, if work is being done on the object will move in such a direction that it is in the same moves in the same direction as the force. Okay, so let me ask you, right, if let's say I have a cube that is floating in mid-air. Okay, I'm exerting a force in this direction, right, and the cube should move in this direction as well. Okay, and if this is the case, right, then yes, the force has done work on this cube. But if the cube somehow moves upwards, right, then we know that this force here is so negligible that in fact, right, there's a much larger force that's doing work on the cube and it's actually pushing it upwards. Okay, so technically this scenario won't happen if this force that I'm now written in white, right, is so negligible, right, the object will move upwards but yet slightly to the right, so maybe something like this, like 89.9 degree kind of thing. Okay, so maybe this is like 89 degree. Okay, but anyway, you all get the idea that the idea is this. Okay, that let me erase this. Okay, that object must move in the same direction as force. Okay, I forgot the word direction, so let me add that in, same direction as the force. Okay, so object will move in this direction. Okay, so object will move. Okay, that's the idea. Now you might want to then put a parallel here, because since they are moving on the same axis. Now because right, there is another formula that's exactly like this, also written as force times distance, and this is moments, our previous chapter, right? Moments, the force and distance, the distance is perpendicular to the force. Okay, so please look back at the previous video if you do not know how to solve for moments. Okay, but I'm not going to talk about moments, I'm just going to talk about work done here. Okay, now work done equal force times distance. Now there are a few meanings to this. First thing, okay, what's happening to the screen? Okay, first thing, work done equal force times distance, right? We have to identify the term work done on object and work done against something. Okay, so work done on something, work done against something. Okay, so first thing, let's look at this work done on object. Work done on object is simple. Let's say I have a box, I push it here, okay, and the final motion is that the box eventually moves in this direction as well. Okay, so there's work done on the box. Okay, it's like pushing a box forward. Okay, so the final outcome is that the box will end up here. So work is done on the box, and let's say from the back of the box to the back of the box in his new position is about 4 meters, and let's say this is 5 newtons. Okay, the work done is simply 5 times 4, which is 20 joules. Now then we have to come up with the concept what is work done against on the box. Okay, so work done against the box will be a force that's opposing the box. Okay, maybe this is 3 newton. Okay, so throughout the entire journey, right, this 3 newton, which is very obvious what kind of force this 3 newton is. Okay, yes, it's friction. Okay, this 3 newton is constantly acting on the box. Okay, so the work done against the box, right, is work done against friction. Okay, because the box is going to do work against the friction, is given by 3 times 4, which is 12 joules. Okay, can? So this is the idea of work done, which is fairly simple. Now let's link everything up that we've learned up to this point to this thing called the work-energy theorem, right? So what is work-energy theorem? Work-energy theorem forces us to consider this. Forces us to consider that the final or rather the initial energy must be the same as the final energy. Okay, and so far in this chapter you have learned 3 things, right? You have learned the first one, which is our KE. You have learned the second one, which is our GP, and you have learned the last one, which is our work done. Okay, maybe on the box or whatever. Okay, so now maybe you're going to start off at a question where the object is already moving and it's at a certain height, as given a force that is pushing it. Okay, and therefore it fulfills all these 3 criteria. Because does it have speed? Yes. Is it on a certain height? Is it at ground zero? No. Okay, it has a certain height. Is there a force acting on it that causes it to move? Yes. Okay, if such is the case, right, then yes, you have all of these 3 components. Okay, but basically the initial energy is the summation of all these 3. Okay, so KE plus GP plus work done. Okay, in some cases this can be 0, this can be 0, and maybe this is like 5, so the initial KE is 5. Okay, in some other cases the KE could be like 2, the GP 2, and the work done 0, so the initial K energy is like 4. Okay, but regardless, right, this has to be equal to the final energy. Okay, so we look at the initial point where the object was, and we look at the final point where the object is. Okay, and we realize that, oh, at that point, right, the KE, the GP, and whatever work done, okay, that's usually this is 0. Okay, by the time it's at its final position. Okay, but in any case, these 3 should sum up to give you the final energy at the final position. Okay, so this is obviously at final position, and this tree, it also should be at the position, but it's known as the initial position. Okay, so let me end off the idea of work-energy theorem with one example. Okay, and we'll actually go back to the roller coaster example, but let me draw the roller coaster more nicely. Okay, let me draw it like aesthetically sound. Okay, and let's solve this question properly. Okay, now first thing, we define this as point B, and we'll define this as point C, and we'll define this as point D. Obviously this is A then. Okay, so same thing, my roller coaster is going to go from A, go down to B, and then loops around. Sorry, can't loop around like this. Okay, so it goes down to A, goes to B, loops around, and goes to D. Okay, now in some questions, right, they may be slightly more tricky, so they will tell you that the radius of the loop is actually r equals to 5. If r is 5, right, then the diameter is 10. Okay, of course this is meters. Okay, now A, right, will be 30 meters from the ground. Okay, so the GP at B and D is very obvious, it's 0. Okay, the first question, right, is, let's say this is a track with friction. Of course there must be friction. Okay, so is there friction? Yes, there is friction. Okay, now I want to know what is the speed of the object at point C. Okay, sorry. Okay, I want to know what is the speed of the object at point C. Okay, so let's start off the question. Okay, so obviously it starts off at A, and then it finally, this is the initial, and finally it will end up at C, which is the final. Okay, so let's start off first at initial. So initial energy, right, equals to final energy. Let's consider everything that is initial first. Does it have KE? Okay, so maybe at A is at rest, so there's no KE. Okay, so let's okay, I'm gonna draw everything in I'm gonna write everything down that is for the initial in green. Okay, so KE at A equals to 0 joules. What is the KE, what is the GPE at A then? It's given by mg30, right, because H is 30. Yes. What is the work done? Okay, at this point there's no work done on it, no one is pushing it or whatsoever, so it's 0 joules. Okay, now I'm going to use rate to denote my final. So KE at C, is there KE? Yes, because I'm asking you to find speed there, so obviously there's a speed there. It will be half mv square. Okay, and this is actually our object of interest, like quantity of interest, that we're going to find this using the work-energy theorem. Okay, so we are interested in V here. Okay, what is the GP at C? Is it at ground zero? No. Is it at reference point? No. Is it at the lowest point of the entire question? No. The lowest point at the entire question is B and D. But now we are looking at point C. It has a certain height and it is 10 meters above ground, so it will be mg10. Now, what is the work done? Now, throughout the entire scenario, right, is it doing work against friction? Yes, it was, right? Okay, because I said this is a friction track. Okay, so let's say the entire distance covered, right, as it moves from A all the way to C, right, is say maybe like, I don't know, let's just call it 100 meters. Okay, and let's say there's a constant frictional force. Okay, so the frictional force acts against, right, so I'm just going to draw my arrow in this direction, and let's say the frictional force is very low. Okay, maybe it's like just 5 newtons. Okay, the work done against friction will be 5 times 100, which is 500 joules. Now, since no one is pushing the cart or the roller coaster forward, okay, there is only one work done, and that's the work done against friction. Okay, so let's sum it all up. What we have, right, will be something like mg30 equals to half mv square plus 10 mg plus 500. Okay, and with this we can actually solve, right? Then you have 20 mg minus 500 equals to half mv squared. And if I give you the mass of the roller coaster, you could work this out. Okay, because g is 10 anyway, so we have 200 m minus 500 equals to mv squared over 2. Okay, and you can work this out on your own if I give you the m, and eventually you'll be able to find v. Okay, so this is how the work energy theorem works. We're going to consider the initial energy and the final energy. Okay, now it's weird, right? If let's say your initial energy, the work done, you say that, oh, initially there's like friction. It can't be, because like if the object doesn't move, right, then can't have any frictional force acting on it initially. Okay, however, let's just up the question by one level. Okay, so let's say indeed, right, in fact, the roller coaster has a booster here, and the booster actually gives it a forward force I'll say 7 newtons. Okay, and in this case, right, the work done on the object, right, initially, right, will not be 0 anymore, because we know it's going to travel 100 meters from A to C, and there's a forward force of 7 on it constantly. It'll be 7 times 100, it'll be 700 joules. That's the initial energy. It's going to be like given to it initially, okay, so that it can complete the entire journey from A to C. Okay, and if that's the case, right, we have to write a 700 here, 700 plus mg30 blah 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 blah. Okay, so this will not be minus 500 anymore, because this will be minus 200. Okay, then this will be minus 200. Okay, which makes sense. Like, you realize the value drop, right, from 500 to 200. Why? Because the forward force is greater, is 7 newton, and the frictional force is 5 newton. It's greater than friction, so obviously the forward force will help to overcome the friction, and that's why the value here, instead of minus 500, it should be will be minus 200. And if we work out now, the v, right, will actually be greater. Okay, in this entire example, you can just use m as like 100 kg or something. Okay, you can assume m to be 100 kg, although that would mean like the roller coaster can only take 2% or something. Okay, so yeah, we are done. Like, if you understand this roller coaster question, right, and maybe you want to try one more question, right, you can actually try this. Okay, so let's say I have a slope. Okay, I should already get a ruler, right? Let's say I have a slope, and I'm actually trying to push a box up from this point all the way to the highest point here. Okay, and this actually 4 meters. Yes, this is 4 meters, and this is actually 5 meters. Okay, now obviously by Pythagoras theorem, this must be 3 lah. Okay, because this is a 90-degree mark. This is a right angle triangle. Okay, now the box itself, it weighs like 2 kg. Okay, and you are trying to move it from point A to point B. Now obviously it's not going to move on its own, so you need to use a force to push it upwards, right? Let's say the pushing force that you give it is at 10 newtons, but then the slope is rough and it has friction, so the frictional force is constant, but it's only at 3 newtons. Now the object at initial position at A, right, is 0 meter per second, but finally when you push it, right, just before it stops, right, at here, right, it is maybe like 2 meters per second. Now, using everything that I've taught you so far, please try to solve or maybe I shouldn't write 2 meters per second. Yeah, you should solve for something, right? So find the final speed of the box when it's at the top, at B. Okay, so if you want, you can try now. Okay, so basically the question is to find V. This is V. Okay, you can pause the video, try yourself. Okay, I'm going to write the solution here now. Okay, so first thing first, initial, right? Initial means we consider everything at A. Okay, first, it doesn't move forward, so it can't do work against friction yet. Okay, but it's going to receive a 10 newton outward force, and we know that it's going to push it over 5 meters. Okay, so first thing, if you have considered 10 Newton, good. But if you have not considered the distance as 5, then please know that, please go back here to the concept of work done and realize that object must move in the same direction as force. And the only way that the object can move in the same direction as 10 as the 10 Newton, right, is that it moves a total distance of 5 meters. Alright, so initially, is that KE? No. Is that GP? No, because it's at the lowest point possible. Is there work done? Yes, and it's given by 10 times 5. We know that you'll have like 50 joules pushing it up all the way. Okay, now final. Okay, I'm going to write in blue. Is that KE? Yes, maybe. Maybe V is not 0. Okay, so let's just assume it's half mv squared. And since m is 2, right? This is just v squared. Is that GP? Yes. Okay, so it has gained a height of 4 meters. Okay, remember GP is on vertical height. Okay, so it will be mgh, which is 20 times 4, which is 80 joules. Okay, something is wrong here. Let's look at it later. Is there work done? Yes, throughout the entire journey is doing work against friction, and the frictional force is given by 3 Newton, so it's 3 times 5, which is 15. Okay, let's sum it all up and you'll see where's the error. Okay, this is 0 0 plus 50, so initial energy is 50 joules, right? Must be equivalent to 80 plus 15 joules plus v squared. Okay, so it's 80 joules plus 15 joules plus v squared. And then you realize something. Hey, wait a minute, isn't this 95 and this is 50? The math will not tally anymore, because what you have eventually will be v squared equals to negative 45 joules. And we know that in secondary school you can't square root a negative number. Even if you square root, right, v is a complex number, which at this point of time it doesn't make any sense. Okay, so this has issues. Now what is the issue? The issue is that the force, right, this 10 Newton, right, is insufficient to produce such a final outcome. Okay, so what can we do? Yes, we can do something. Okay, we just need to increase this force, right? So let's increase this 10 Newton force to 20. Now if we do that, right, then this will be 20 times 5 and this will be 100 joules. So this is 100. Now this makes sense. 100 equals to 80 plus 15 plus v squared. Okay, so v squared will be 95, right? So v squared will be 5. So v will be square root of 5 joules. Square root of 5 meter per second. Okay, so if you have attempted a question, then you got some error, that is good. Okay, because the initial question, right, has this at 10 Newton and it was insufficient to produce such an outcome. Okay, so you should have some error. Okay, you shouldn't be able to find the value of v. Okay, the only way that we can find v, right, is such that this is 20 newtons or slightly below 20 newton. Then we can start to find v. Okay, in fact this has to be like I think 18.5. Okay, but yeah, 20 Newton works. Okay, so in previous question, right, when it was 10 Newton, the force was insufficient. Okay, so now let's go on to the last concept for today, which is the concept of power. Power is the idea of work, the rate at which work is being done. So I'm just going to write energy over time. But knowing that what energy is now, right, it's actually the work that is done on an object. Okay, so maybe at the end of the day it has speed, maybe at the end of the day it has speed, it gained height, okay, it did some work against friction, okay, it gained some kind of energy because someone or something is like pushing it forward. Okay, so it's also possible to say that power is work done over time. Now regardless, right, it is the rate at which you do work. Okay, so that's why a bus engine, okay, is usually more powerful than say the normal grab car engine. Okay, because the bus is like carrying more mass. Okay, so like assume that they are going up a slope, both are going up a slope, and both the slope these two are the same slope. Okay, so by Pythagoras theorem, both are the opposite and the adjacent, they are 3 4, right, which makes them the same slope. So this is a bus, obviously the bus weighs heavier, this is a car. Okay, and both are going to the same point. Okay, and both finish at the same time, within the same amount of time. Okay, we know that this is more powerful, this bus is more powerful because it's able to do much more work in a shorter amount of time, right? Okay, because in the entire process it's like carrying more mass, but within 5 seconds can do that. Okay, okay, so that's the idea for power. And lastly, idea for efficiency. Efficiency is always the ratio of the output over the input. Okay, so everything is inefficient in this world, there's nothing that's 100% efficient. Okay, even as I talk, right, maybe I'm like producing 10 joules, no, that's too high. Maybe I'm like producing 1 joule of energy as I speak. Okay, but like maybe 0.8 joules are like captured to electronic signals and make into like the electronic voice that you hear now, and 0.2 is like dissipated as heat or something. Okay, now even for this bus right over here, the engine right is probably like 30% efficient. Okay, so let's say the engine gives it like maybe 1000 joules of energy, only 300 joules right is used right to maybe go up the hill. The other 700 joules, they are yes, the most common answer, right, dissipated as other form of energy, such as your heat, your sound, etc. Right? Okay, so I'll end the video here, and I'll upload this file somewhere. If you need, please text me for the link of for this file. Okay, with this I'll end my video.